Dear viewers, welcome back to our Learn Easy series. In this lecture, let us learn about Euler's crippling load for columns with both ends fixed. So we have column with both ends fixed. This is a fixed support and this is fixed. A and B are fixed. Load P, and we know that in case of fixed support, there will be three reactions: one vertical reaction, one horizontal reaction, and a moment. So we have marked the load, and we are marking the moment at the fixed end as m naught. So P is a critical load and Y is the deflection at any section X. We are considering a section XX at X distance from A. So this is the deflection. Y is the deflection at XX. M naught is the fixed end moment at A and B. So it will be having moment here as well here. Wherever we have fixed support, it will be having end moments. So let the end moment be M naught. Now we need to take bending moment about this point, at this point. So bending moment at this point will be equal to, say here, let us take from this side. So we have load P, distance is Y, and this will produce anti-clockwise moment, therefore minus P into Y. And we have already an existing moment at the fixed support M naught, so plus M naught will be there. So minus P into Y plus M naught is the bending moment at XX. So this will be equal to M naught minus Py. We have the differential equation Ei d square by dx squared equal to mxx is the differential equation for flexural problems or beams with bending. So Ei d square by dx squared equal to mxx, which is equal to M naught minus Py, which we have arrived here. So M naught minus Py. So bring this Py this side. Therefore, Ei d square by dx squared plus Py equal to M naught. So dividing the entire equation by Ei throughout. So we'll be getting d square by dx squared plus P by Ei y equal to M naught by Ei. So for this we need the differential solution for this differential equation, that is solution for y. So the general solution of this differential equation will be y equal to a cos x root p by Ei plus b sin x root p by Ei plus M naught by P is the additional term. See, we have seen in the earlier derivations, we will be getting a cos x root P by A plus b sin x root P by Ei for both ends hinged. And one end fixed and other end free, we got a cos x root P by A plus b sin x root P by Ei plus small a. In this case, we have M naught on the right side, this P will go this side. So M naught by P will be the additional term. So y equal to a cos x root P by A plus b sin x root P by A plus M naught by P. Now we need to find the constants. So A and B are constants. So the constants shall be found using the boundary conditions. So when in case of fixed columns or fixed ends like this, so at the fixed end we very well know that slope and deflection are 0. Similarly here also slope and deflection is 0. So at A, that is when x equal to 0, y equal to 0, that means at x equal to 0, deflection is 0. Similarly, at x equal to 0, dy by dx equal to 0, that is slope is also 0 at this support. Similarly, deflection is 0 at B and slope is 0 at B. So actually we have four boundary conditions: when x equal to 0, y equal to 0, when x equal to 0, dy by dx equal to 0, then when x equal to L, y equal to 0, when x equal to L, dy by dx equal to 0. These four boundary conditions shall be utilized to get the constants. However, we will be using the three boundary conditions as shown here. So the boundary conditions are when x equal to 0, y equal to 0, that is deflection at A is 0. When x equal to 0, dy by dx equal to, that is slope at A is 0. When x equal to L, y equal to 0, that is deflection at the end B is 0. So using boundary condition 1 here, that is put x equal to 0 and y equal to 0, we'll be getting 0 equal to A cos 0 is 1. So A sin 0 will get cancelled plus M naught by P. So A plus M naught by P equal to 0. Therefore, A equal to minus M naught by P. Then to employ this second boundary condition, we need to find dy by dx. So dy by dx will be equal to A, say if you differentiate cos x root P by A, this will be sin x root P by Ei multiplied by root P by A, because we need to differentiate apply the function of function rule. So if you differentiate this and then this with respect to x, you'll be getting root P by Ei plus b sin x root P by A. This will be a cos, if you get minus sin x root P by A and into root P by A. Here b sin x root P by A, when differentiated, will be getting cos x root P by A into x. This will get cancelled because we have it's a constant. So here minus a sin x root P by A into root P by A plus b cos x root P by A into root P by Ei. This will yield equation 2. In this, we'll substitute the second boundary condition, put x equal to 0 and dy by dx equal to 0. So it's 0 on left side. We'll be getting x equal to 0. This will get cancelled. B cos 0, cos L root P by B say if you put x equal to, say this is a boundary condition, x equal to 0. So b cos 0, b into root p by a. So b root p by a equal to 0. Either b should be equal to 0 or root p by a should be equal to 0. So we need to examine which should be 0. So root p by a cannot be 0 because p, when it is 0, p will be 0. So since there is applied load, p can't be 0. Therefore, b can be equal to 0. Therefore, the equation becomes y equal to, we have got a as minus m naught by p. So minus m naught by p cos x root p by a plus m naught by p. So taking m naught by p as a common term, we are getting 1 minus cos x root p by ei. Now we can use the third boundary condition, that is put x equal to L, y equal to 0. So put y equal to 0 on this side. So m naught by p into 1 minus cos L root p by ei. So 0 equal to m naught by p into 1 minus cos L root p by ei. Therefore, this will indicate cos L root p by ei should be equal to 1. Then only you will be getting this satisfied. So cos L root p by a equal to 1. So this is possible when L root p by a equal to 0, 2 pi, 4 pi, etc. Because we know that cos 0 is 1, cos 360 is 1, likewise it will go. So 0, 2 pi, 4 pi, etc. So from this, taking the lowest significant value or least significant value, we can't take 0. So least significant value is 2 pi. Therefore, we'll be getting L root p by a equal to 2 pi. Squaring on both sides, you'll be getting L squared p by a equal to 4 pi squared. Therefore, p equal to 4 pi squared Ea by L squared. This will be the Euler's crippling load for column with both ends fixed. Thank you, viewers, for subscribing our channel and making it reach many. Thank you.